All right, testing, testing. Cool. Let me check YouTube real quick. We're live, right? Yes, we are. We are indeed live. All right. Sure. Oh yeah, so we're gonna be doing some programming on the Atari. We're gonna try and learn that. Learning tends to be pretty straightforward, so we'll probably be successful, but you know, got into a little bit of doubt here and there. And I'm going to be using this lovely PDF to start out with, which is for newbies, and I'm a newbie, so let's get started then. All right. Right, and this is just an introduction. I read a little bit of this. This is just kind of an introduction. Right. And then this is kind of an introduction to the entire system as a whole. Yes, he mentions that it has a 6507 CPU, has a little bit of memory, RAM for actual, dynamic calculations, and then ROM for read-only memory. And yeah, there's various I/O that you can have. If I remember correctly, Atari has like some custom peripherals that you can use, but yeah, for the most part, joystick and paddles are standard. Well, joysticks especially standard. All right, and they say it's a 6507, but it's mostly a 6502. Right, and there's a lot of limitations. You only have 128 bytes of RAM and 4 kilobytes of ROM. Very fun. Right. Okay, that's just reiterating the I/O devices. Okay, and it's what you need. Yeah, this is it's very standard. You have a text editor, assembler, blah, 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 blah. And then there's DASM, which I don't happen to have. I heard about it, but I heard that WLA is also an alternative, and I kind of used this a little for Game Boy Color development, so I'm a little bit used to it, and so we'll see how that goes. When we try to use WLA for the Atari. And right, there's the emulator. Right, there's Stella, which... Oh, oops. Flip that. I actually have it already downloaded. Let me get that. Yeah. So now I don't have to re-download it every time, which is a good thing. Right, so anyways, Stella's somewhere. Oh, oops. There we go. Right, so I have a test game here. It might be ideal to actually turn on desktop audio. I normally keep this off because I listen to just whatever music in my free time and don't really want to bother anyone with it. But we can turn it on just for the sake of Or actually, what I can do... I was going to say if I would... I don't want to infringe on any copyright, so I was going to pull up NCS for any music. But what I can actually do is... I'll probably do that anyways. But what I can actually do is I can enable it and then pull up Stella. Right. Alright. Right, so like sound works and stuff like that. And that's cool. And then you can disable that again. And I won't have to do that a lot, so it won't be too invasive in terms of the overall viewing experience, hopefully. Okay. So to summarize, yes. Yep, we have these things. I mean, we don't have the bookmarks, but we have the essentials at least. Stella Programmer's Guide. Oh, okay, cool. Sure, so if I have any questions that's not answered by this, I'll definitely take a look at that. Okay. We're not going to cover a lot of specific 2600 specific stuff this time, but this is mostly stuff you need to know. Television has been longer than you probably realize. Early mechanical television pictures were successfully broadcast in the 20s and 30s. Yes, really. See this thing. I believe them. Yes. I don't even think that's a particularly surprising statistic. Anyways. The mechanical scanning technology utilizing these early television systems are no doubt the predecessors to the scanning employed on modern televisions. A television doesn't display continuous moving image. In fact, television displays static non-moving images in rapid succession, changing between images so quickly that the human eye perceives any movement as continuous. Okay, right, yes, that's how TVs work. Atari 2600 console was released in many different countries around the world. Not all these countries use the same television system. Right, so the Atari has to do like some translation in terms of TVs, in terms of games to TVs. Right. Okay. Oh yes, and this is an important point. I remember there was actually an incompatibility between NTSC and PAL and other units for sharing cartridges. We'll stick with NTSC, I believe. Television signal contains either 60 images per second or 50 images per second, right? This is closely tied to the frequency of mains AC power in the countries which use these systems, and is probably for historical reasons. Furthermore, NTSC images are 525 scanline deeps, and PAL images are 625 scanline deeps. Right, there was a difference in scanlines. I remember this was also important last time I looked at this. Okay, this is not completely blind, but I've never actually programmed a game before on this. I just kind of looked at it very briefly. NTSC images have less detail but are displayed more often, right? In practice, it looks pretty much the same, sure. From the 2600 point of view, right, the difference in frequency and the resolution are very important because it is the programmer who has to control the data going to the TV. It is not done by the 2600. The 2600 only generates the signal for a single scan line. This is completely at odds with how all other consoles work, and what makes programming the 2600 so much fun. Not only does the programmer have to worry about game mechanics, but she also has to worry about what the TV is doing, i.e. what scanline it is drawing and when it needs to start a new image, etc., etc. Let's have a look at how a single image is drawn by a TV. A television is a pretty amazing piece of 1930s technology, agreed. It forms the images we see, but okay, blah, 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 blah. Oh, right, this is how, like, TVs work. They go from, like, there's, like, scan lines, and they go from, like, top left, and they keep going, and then there's a concept called H blanks and V blanks. Yeah, it's all very fun. Turning off and repositioning process is not instantaneous, right? That's what we call at the end of a scan line and at the end of an image. Right, this is called H blank, this is called V blank. That's the sort of repositioning thing. Right. Oh, and they even explain it. Right, this is the H blank and this is the V blank. Or horizontal blink and vertical blink. If very complex but simple to understand, okay. I'm just going to kind of skip this stuff. The thing is, I don't want to skip too much in case something's actually important. The encoding of the color information for the TV signal gives some interesting combinations of Atari and games, for example. The upshot is that a single frame of a TV is actually only half the vertical resolution of the image. Okay, interesting. The extra 0.5 of a line is used to indicate to the TV if the frame is the first or the second image. Oh, there's interlacing. Right, yes. I remember interlacing. Yep. Yeah, by the way, if you want to know more about H blanks and V blanks and interlacing, I suggest you just kind of look those things up. I'm not really going to go over them in depth. Oh, cool. The Stella community actually figured out how to use interlacing to their advantage on the Atari. That's very neat. Okay. The actual depth of a single frame is 262 and 312 pounds. Okay. Now, if TVs aren't told that a frame is odd, they don't offset the first scan line by half the scan line's depth, and so scan lines on successive images or successive frames are exactly aligned. We have a non-interlaced image displayed at 60 and 50, and this is the standard format. An Atari 2600 frame sent to a TV. In summary, okay, an Atari 2600 frame consists of 262 scan lines or 312 scan lines scanned at 60 Hz or 50 Hz. It is the job of the 2600 programmer to make sure that the correct number of scan lines are sent to the TV at the right time with the right graphics data, and appropriate control signals to indicate the end of the frame are also included. Okay, that's good to know. Yeah, it's good to know that we actually operate based on interlacing instead of the full scan lines. One other aspect of the difference between TV standards and a consequence of the incremental development of television technology. First we had black and white and then color was added, but our black and white TVs could still display a color signal in black and white, right? That makes sense. Is that color information is encoded in different places in the signal for NTSC and PAL. So even though the programmer is fully responsible for controlling the number of scan lines per frame and the frequency at which frames are generated, it is the Atari itself which encodes the color information into the TV signal. This is the fundamental reason why there are NTSC, PAL, and SECChem Atari systems. The encoding of the color information for the TV signal. We get some interesting combinations of Atari and games, for example. If we plug in an NTSC cartridge to a PAL 2600, then we know that the NTSC game is generating frames which are 262 lines deep at 60 Hz. But a PAL TV expects frames 312 lines deep at 50 Hz, so the image is only 262 of the 312 of the correct depth, and also images are arriving 60 over 50 times faster than we expected. If we were playing on an NTSC TV, then the PAL console would be placing the color information for the TV signal in a completely different place than the TV was expecting. So we would see our game in black and white. Oh, okay, because the color information is not placed at the right thing. Interesting. Okay. Okay, there are several combinations you can play with. The essence is that if you use a different 2600 variant than TV, you will only get black and white, as the color information is not in the correct frequency band of the signal. And you plug in a different cartridge than TV, example NTSC card with PAL TV or vice versa, then what you see depends on the television's ability to synchronize with the signal being generated, as it is not only the incorrect frequency, but also the incorrect number of scan lines. How fun! All this may sound complicated, but all we really need to do is create a kernel, which is the name of your section of an Atari 2600 program, which generates the TV frame, which does the drawing correctly. And once that's working, we don't really need to worry too much about the TV. We can abstract that out and think about what we want to draw. Well, I lie, but I don't want to scare you off too early. Next session, let's have a look at how the processor interacts with hardware I/O and memory. Finally. Okay. The TIA and the 6502. Spend this session having a look at how some of the hardware generates a scanline for a TV. Remember in session 2 we had a good look at how a TV works, and in particular how a TV frame is composed of this number of scanlines. It is the programmer's job to control how many scanlines are sent to the TV, but it is the 2600 which builds the actual signal, comprising of color and intensity information for any scanline. This color and intensity information is derived from the internal state of the TIA, television interface adapter chip inside the 2600. The TIA is responsible for creating the signal for a single scanline on the TV. The TIA draws the pixels on the screen on the fly. Each pixel is one clock. 1 clock of the TIA's processing time, and there are exactly 228 color clocks of TIA time on each scanline. But a scanline consists of not only the time it takes to scan an electron beam across the picture tube, but also the time it takes for the beam to return to the start of the next line. Right? Horizontal blank. Of the 228 color clocks, 160 are used to draw pixels on the screen, giving us our maximum total horizontal resolution of 160 pixels per line, and 68 are consumed during the retrace period. The 6502 clock is derived from the TIA clock through divide by 3. That is, for every single clock of 6502 time, through divide by 3. For every single clock of 6502 time, 3 clocks of TIA time have been passed. Ooh, okay. Therefore, there are exactly 228 over 3, which is 76 cycles of 6502 time per scanline. The 6502 and the TIA perform complex in-step dance, 1 cycle of 6502 and 3 cycles of TIA. A side note, 76 cycles per line times 262 lines per frame times 60 frames per second equals the number of 6502 cycles per second for NTSC, which is 1.19 megahertz. Okay. So as our 6502 program is executing its instructions, the TIA also is sending data for each scan line. Every cycle of 6502 time, we know that the TIA sends 3 color clocks of information to TV. The TIA was the first 68 color clocks per scan line, then the horizontal retrace period. It was in the horizontal retrace period. If it was in color clock 68 to 227, then it was drawing pixels. And so we go. 6502 program is doing its stuff, and at the very same time, the TIA is doing its stuff. The magic happens when you start changing the state of the TIA, because those changes are reflected immediately in the TIA output of the TV. Since the 6502 is locked to the TIA through their shared timing origin, it is possible for the programmer to know exactly where on a scan line the TIA is currently drawing, i.e. what pixel. And knowing where the TIA is at allows us to change what it is drawing at particular positions on the scan line. We don't have much scope for change, but we do have some, and it is the ability that master 2600 programmers use to achieve all those amazing effects. Naturally, to achieve this sort of precision timing, programmers have to know exactly how long the 6502 takes to do each instruction. For example, load store combination takes a minimum of 5 cycles per 6502 time. How many on-screen pixels is that? Remember, 3 color clocks per 6502 cycle, so that's 3 times 5, which equals 15 pixels. Essentially, if one were using the quickest possible load store combination to change the color of, say, the background, then the absolute quickest this could be done would be every 15 pixels, i.e. just on 11 times per scan line. Don't despair. It's not necessary for you to learn how to count 6502 clock cycles at this stage. These sort of tricks are for more advanced 2600 programming, and the original design of the TIA hardware made this unnecessary. It's only when you need to push the hardware beyond its original design you will come to appreciate the benefit inherent in the way that the 6502 and the TIA are intricately tied together. Next lesson, we'll have a closer look at the TIA and how it determines what color to use for each pixel scan line it is drawing. In particular, we'll start to look at background, playfield, sprite, missile, and ball graphics. Oh, they actually started to do code here. Okay. Oh, and they started to actually do that. Okay. Interesting. What sections do we still have? TIA. I think I'll just do session 4, and then I'll see if I can do something myself. I just kind of want, because like I know how to program things, I just kind of want an introduction to the hardware at least. TIA determines the color of each pixel based on its current state. As soon as the TIA completes the scan line, begins drawing the next scan line. Unless there's some change to the TIA's internal state during the scan line, then each scan line will be completely identical. Consequently, the absolute simplest way to draw 262 scan lines for an NTSC frame is just to wait. Right, after that time, the TIA will have sent 262 identical lines to the TV. There are other things that need to add appropriate controls to the signal frame so that the TV would correctly sync the frame. But the essential point here is that we can leave the TIA alone and let it do its stuff. Without our intervention, once the TIA is started, it will keep drawing scan lines all the same to the TV, and all we have to do is draw in scan lines. It's time to have a little introduction to the 6502, right? So the CPU is a 6502, 8-bit processor, right? We know this. I know this. 8-bit binary, yeah, okay, I know what binary is. I know the difference between decimal and binary. I know what hexadecimal is. Okay, it has 3 registers, so I actually already knew this. A, X, and Y. Right? An accumulator, and then these were like certain special registers. Remember this? What can you do with 3 registers? Not much, but a hell of a lot, not much. Adds up to something, right? A lot of work is left to the programmer. The 6502 cannot multiply or divide. I knew that. It can only increment, decrement, add, and subtract. It can only work with 8-bit numbers. I knew that as well. It can load the data from one memory location, do one of those operations on it, and store the data back in memory. Yep. And out of that capability comes all the games we've ever seen on 2600. Amazing, isn't it? Yeah, that is pretty cool. Kind of got used to it when programming other processors, but yeah, that is pretty nice when you think about it. At this stage, it's probably a good idea for you to start looking at some books. Right? Every bit is sacred. Only the human mind is currently capable of writing programs that sufficiently as required for 2600 development. Okay, that was a bit of a diversion. Right. Which actually I'm not that familiar with 6502 programming, so I don't know if a book's the best option, but I'll definitely take a look at the instruction set and see what each individual thing does. That was a bit of a diversion. Let's get back to the TIA and how the TIA and 6502 can be used together to draw exactly 262 sand lines on our TV. Our first task is to simply wait for 76 cycles times 262 lines, right? Simplest way to just wait on the 6502 is to execute a NOPE instruction. NOPE stands for no operations and takes exactly 2 cycles to execute. So if we had 38 NOPEs one after the other, the 6502 would start executing the last one exactly 76 cycles after it started the first. And assuming the first no op started at the beginning of the scan line, then the TIA, which is doing its magic, at the same time would have finished the last color right. In other words, the very next scan line will start as our 6502 is just about to execute the last instruction after the last nope, and the TIA was just about to start the horizontal retrace period, at which as we have learned is 68 clocks long. How do we tell the 6502 to execute a nope? Yep, just say nope. Same as on the 6502 as it is on the C80, x86, ARM, blah, 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 blah. Yeah. Above code shows 2 nope instructions. The assembler is case sensitive. Okay, right, it's just assembler things. When the 6502 receives this opcode, right, there's opcodes for this stuff, and that's the nope opcode. But there are better ways to wait 76 cycles. After all, 38 nopes would cost us 38 bytes of precious ROM, and if we had to do that 262 times without looping, that would be 9432 bytes, more than double the space we have for our entire game. Right, obviously. The TIA is so closely tied to the 6502 that it has the ability to stop and start the 6502 at will. Funnily enough, at the 6502's will. More correctly, the 6502 has the ability to tell the TIA to stop it. And since the TIA automatically restarts the 6502 at the beginning of every scan line, the very next thing that the 6502 knows after telling the TIA to stop the CPU is that the TIA is at the very beginning. The beginning of the very next scan line. In fact, this is the way to synchronize the TIA in the 6502 if you're unsure where you're at. Simply hold the CPU through the TIA, and next thing you know, you're synchronized, just like a time warp or a frozen sleep. Maybe you're simply not aware of the time passing. If you say halt and then continue on as if no halt has happened, you say halt and then continue on as if no halt has happened. It has, but the 6502 doesn't know it. This CPU halt is achieved by writing any value to the TIA register, quote-unquote register, called WSync. Right, I think they mean like a hardware register, like you typically see in this sort of programming, which is not technically like a CPU register, but it is considered a register, yes. Before we get to reading and writing values to and from registers and memory, and what that all means, we need to have a look at the memory architecture for the 2600 and how the 6502 interacts with memory, including RAM and ROM. Okay, I think did we have a section about like graphics or something like that? Or maybe that was later on. I don't remember. Oh, wait, no, it was in the other document. Okay. Wherever that was. Should be downloaded. Yes, Stella. Stella Programmer's Guide. Alright. Okay. Right, so there's a bunch of registers. Okay, so playfield, that sounds basic. How about yeah, let's look at how the playfield is done. Yeah, okay. I'm getting really lost in this document. Yeah, so how about we go to like 7 or something? So it was page 5, right? Yes. Oh, interesting. How about we actually write a color to the background? That would be at least something. Yeah. So if that register is set, both that will be drawn. Yeah, let's have it draw like a red screen or something. That could be cool. Does it tell you how memory is laid out? Yeah, probably the PIA. Oh, I guess I could also kind of skip to the kernel and see how that's done. What I'd like to know is a memory map. Oh, I guess the memory... I guess the section I literally just skipped would probably be helpful. Sure. Perfect, yes. Exactly what I want. So that's the memory map. And... Oh, that's interesting. The TIA registers and RAM are all in the zero page, which is a special thing that you can look up about the 6502. Okay. Yeah, generally WLA has a lot of special directives, which is useful to know. So there's all these groups. Huh. Yeah, because you can like see they have a lot of special headers like the GB header and SNES header. I actually don't know what SMS header is. Sega Mega, well, SMD is Sega Mega Drive. What is SMS? SMS console? Oh, Sega Master System. Okay. But yeah, that's interesting. Here's the memory map definition. Okay. So there's an org. Directive. Yeah, that's like typically that's typically used to denote the starting address of like your code in ROM, so that's important. Okay, I kind of want to. Yeah, I kind of want to see what the kernel is, what it sort of looks like again. Right. Oh, that's interesting. Oh, I think what's actually happening here is maybe the top 3 bits or the top 3. Yeah, I think it's the top 3 bits of the address are unused. Right, this is exactly what I was wondering. I was wondering if there was like an interrupt vector, which there is actually. I wonder if they mentioned it at all before. No, I think this was like the first time they mentioned it. Okay, sure. let's get right to it. Finally, yes, we'll say org. Was it .org? Yeah, it's .org. How about entry? Yeah, I probably want to do. Probably want to get some addresses at this point. I actually think I want to use ink. Okay. Yeah, H sounds like I'm programming C, which is a bit weird. Okay, if I look here again. Okay, yeah, interesting. I think sometimes you see with like a lot of other consoles that there's typically like a predefined header. Like we go to .gv header. Like you'll see like Game Boy Color games have like an actual specific header that they need to fill out, otherwise they're not valid games. And that doesn't look like the case for the Atari, which is nice. It's sort of a little bit annoying to fill this stuff out. Okay. Is there an include macro? There is, yes. Not include. So I can say dot include, or no. Okay. So I would say dot include vcs.inc. Let me v-split it. I want like a define or something like that. Not that, not that. Maybe a dot equal? That doesn't seem it either. Is it dot define actually? I'm actually unsure at this point. Yes, that actually is what I want. Okay. Because what I want to do is I want to okay. How about it for WSync? Do you have okay, great. So yes, WSync does that, but where exactly is it? Oh, cool. These are the addresses. Got it. So I can say define WSync 2. Yeah, it was 2. Oh, what does vblink and vsync do? Sure, let me look that up. So vblink. This address controls vertical blink and latches and dumping transistors on the input ports by writing to. So writing 1 to this starts the vertical blink and 0 stops it. Do I need to stop it at some point? Okay. So this is at the start of the frame. Okay. So then I load. Wait, okay. This seems to stop vertical blink, right? That actually stops it. Okay. And then does other things that I'm unsure about. We'll just incant the ancient incantations and hope it works out. Define vblink 0. Define vsync 1, if I remember correctly. So this probably loads to the A register and that stores it into vblink. Makes sense. This starts vblink and this or stops it, I guess. Okay. So this would start vsync, and then that lasts for 3 scan lines, I guess. And then with WSync, you can just kind of write whatever, if I remember correctly, right? Yeah, you can just write whatever. Wait, I think I remember you use cache line. For that, SJV sync. And then 37. Okay. I mean, loops should definitely be possible on the on the 6502. Hold on while I sort of look that up. 6502 makes oh. There should also be a nice table somehow. Yes, okay. Yeah, so there's actual loops. So let's see, we wanted to do like 37 or something like that? Yeah, that seems good. Wait, how do I decrement? Is there a specific instruction for decrement? Because I wouldn't be surprised if they're just, Yes, there is a specific instruction for decrement. Maybe if I look it up, dec. And it looks like it can only be done on memory, which should be fine. We just didn't devote a byte to how many we want to the blank, and that's okay. There also seems to be specific instructions, so I could do. Right, if I was struggling with memory, I could just do something like this. And add with carry. But aren't there actual like subtraction instructions that don't use carries? Can I clear the carry flag? If that's not the case, can I clear the clear the carry flag at least? My gosh, so tongue-tied. How about I make a function called h blank wait. And then I should be able to call that function, right? We still have stacks on the 6502, right? Call. Maybe they call it a function? Subroutine? JSR. Okay, great. And then we'll say JSR JSR H blank wait. And then H blank wait takes its argument in the A register, and we'll do something like subtract. What is it? Or I'll do, okay, CLC, and then we do H blank wait loop. We'll do something like that, and then did I already lose it? No, okay. Oh, interesting. So that actually does set that set the 0 flag as well. I was wondering if it did that. Yeah. So the 0 flag is set. That's cool. Does a return instruct? Is it RTS? Yes, let's go. I think I've actually looked at the 6502 instruction set before, which is why I can sort of was able to guess that. So branch if equal H. Wait, no, I don't want a branch if equal. I want a branch if not equal. They're called BN. Yes, BNE. Okay. BNE H blank wait loop. Yes. So now this should successfully wait as long as I want it to. Right, we can just store whatever in wsync. Okay. Oh, right, and this is to wait on vertical blank. Sure, that makes sense. Oh, so they're actually writing to the color of the background, but they're making it a different color every time. That's interesting. That's very cool. Right, I keep forgetting. Actually, we don't always use cache signs here. We use decimal to, or we leave out the cache sign for decimal, but we put it in for hexadecimal. And then LDA. I'm gonna make this. Okay, so we want to do this 192 times. Sure, we can do that. Render loop INX STX. So I'm going to do the same trick. I'm going to continue using SBC, and then we can say branch if not equal to render loop. All right. Ah, so then we enter the blanking mode. Nice. Which blanking mode is entered by writing two to vblank, right? That's what they did in the kernel, right? 2 and 6. Why? Enable latches. Okay, I guess you just have to enable the latches. Sure, whatever. That makes sense. Not really, but again, we'll just do the magic incantations until we figure out what's going on. Actually, yeah, decimal's more intuitive there. Wait, no, that one I actually wanted to be hexadecimal, right? Because it was vsync. And then there's 30 lines here. Okay, that should work. Hopefully. Let me just recheck that the registers are what I think they are. Zero, 1, 2. Okay, great. Let's see if it assembles. ROM banks and ROM bank. Oh, right, sure, whatever. What was it? Dot ROM bank map. What is it that they exactly wanted? So ROM bank map. Okay, sure. It'd probably be better to put it in the include file. .rom bank map. Banks total 1. Bank size, was it? I think it was hex 1000. Yes. Banks. So banks total tells the total amount of ROM banks. It must be defined by. Banks tells the amount of banks that follow and that are of size bank size, which has been previously defined. Oh, okay. So what I could actually do is instead I could say .rom banks 1 and .rom bank size is 1 x 1000. Okay. Sure, let's try it now. No ROM bank size defined. Oh, I have to do it the other way around. Sure. WA 6502 became ASM. F0. It does? How? Okay. How do I say bank start at a certain place? I'm very confused. Do I have to explicitly define a memory map instead? I have no idea. Memory map. Maybe, actually. Begins the memory map definition. Using memory map, you must first describe the target system's memory architecture to WLA before it can start to compile the code. Memory map gives you the freedom to use WLA to compile data for numerous different real systems. Examples. This is like the first time I thought I'd say I actually kind of miss linker scripts and in GCC and Clang. Okay. Okay. I guess this is sort of what I want. This kind of looks like what I want. Okay. Dot memory map default slot I guess my default slot is 1 and then no, not that. Okay. Slot size is hex 10. Well, maybe not. Slot 0. What is this? This was like TIA or something? TIA slot 1. RAM slot 2. ROM dot end me dot end me. That's what I'm feeling right now. Oh, and the default slot should probably be 2 in that case. Okay. Okay. ROM bank. Know that you can use ROM bank size and ROM banks. The thing is, I'm very confused. Like, how do I say that the ROM bank is actually at the end of the ROM? I don't really know how to say that. Okay, also there was like, right, okay, so .org .word is a thing. Here. Yes. Is .word 16-bit? .word is an alias for .dw. .dw defines words 2 bytes each. Okay, sure. Let's use DW. And then we'll say, yeah, everything's entry. Entry. ROM. Can I say forget the wrong bank, actually? How do you do comments? Oh, okay. So you can just do that. Cool. What was it? Ding. Nope, you need them. Base. Oh, is this what I want? Defines the base value for a bank number. Oh, okay. Maybe this slot is only for padding? I'm really not sure. It doesn't feel obvious. Okay. So I guess you say 2 banks, and then bank size, or dot from bank map, probably. Bank size, banks 1, bank size, banks 1, dot end row. Couldn't parse. What? Oh, because you're not supposed to have that, yeah, right. Couldn't parse from banks. Oh, it's banks total. I think it's time for a little bit of music for me. What do you mean? I don't want to do bank 0. Okay, let's see, split this. Dot bank 1 slot 2. Do I have to write it? It still overflows. What do you mean overflows from bank 1? Didn't I just say to not... Wait. No, I didn't say that. I said to use... Wait, so there's different... So with the memory, there's different slots. And then you have different banks. I think I'm just really brain damaged. It's... I can't wrap my hand around this stupid thing. Okay. This is okay. Yeah, I'm actually brain farting right now. Okay, it describes the slot and its starting address. Slot numbering starts at 0 and ends at 255, so you have 256 slots at your disposal. This is straight directed. So that's memory map, right? So what is it, bank 2? It's probably bank 2 at that point, right? ROM banks is equivalent to 2, but I selected bank 2. Right. Okay. Oh, do I have to use Orgay or something? Origin overflows from bank. Okay. Wait, maybe that was it, actually. Okay, sure. That works. Whatever. Alright. Let's link it. Game.link. Objects. Game.o. WA link. Or no, there's no dash in there. Okay, just WA link. Game.link. Yay. No. Oh, right, because I have to say game.bin. What? But I defined it, didn't I? Oh wait, no I didn't. I remember now. What is that? What is that register? That register is 9. Dot. Should be using cache line for these two because they're actually hexadecimal addresses, so that makes that easier to identify. Colubk equals 9. Yay! Okay, let me do a good old hex dump just to make sure I'm being overall sane. Right, and it's little endian, so it's little byte, big byte, right? Okay, that looks approximately right. Wait, no, that's not approximately right. I wanted to this. I'm so done. Yeah, I want this to only be... Okay, maybe if I say 1... and then WLA 6502 game.asm. Oh wait, okay. Game.asm. So I want ping 0. Please. WA or WA link. Okay. Let's do another hex dump. There we go. Oh my gosh. Finally. Yay. So right, let me pull up Stella. Alright, go to my desktop, go to Homebrew, Atari, Pong Remake. We're gonna play the game. Oh no, invalid instruction. How could this happen to me? Okay, right, okay, that looks good. So this is a disassembly of RAM. How do I get a disassembly of ROM? Actually, how did this happen? Can I reset it? Oh, cool. Okay, so I can do... Oh, okay, so that did that. Yeah, that's the code I wrote. What does CXMOP mean? What? Wait, okay, let me look at the instruction set. Because if I had to guess about what I just did... Oh... I specified addresses. That's fun. Alright, let's... So we need to put hashtags, I'm guessing. Yep. Yep. Hashtag, 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 hashtag. All right, let's All right, can I please exit? Thank you. All right, let's go back. Right, now it looks good at least. Oh, that does one frame. Okay. How do I step? Yes, that one. Okay. Wait. Hold on. Yeah, that doesn't look right. Oh, shoot. Did I switch around VSync and VPlane? I totally did, didn't I? So VSync is 0 and VBlank is 1. Alright, let's do this again. Link, escape, exit ROM, game. Yep, reverse, great. Step. Alright. Yep, so I can see A go down. By the way, I remember using SBC again. Yes, I did. Forgot to do scale C here. That'd probably be good. Can I seriously not do just this simple subtract instruction? That's a little bit surprising. Maybe I'm comparing it too much to other processors, but I still feel like that's a bit weird. But there's not just a plain subtract instruction. Okay. Oh, there we go. So it... What? So it's like sort of invalid, but not really? Weird. Okay. Oh, right. Control S. Yep. Yeah, I'm just gonna... Because I think it should go after... A is 0, but I just kind of want to make sure manually. Right, so that return... Okay, yeah, so that behaves how I thought it should. Wait, hold on. Okay. So CLC should clear the carry flag, right? Like it did below, right? I'm sorry, let me see SBC again. So you subtract 1, right? That should be 1 subtracted. That is bizarre. I have no idea why that happens. Oh, that's cool, and it also shows you the dot. This is bizarrely confusing to me. Okay, let me see SBC again. SBC, just any SBC. What does that even mean? C negative. Yep. Okay, so I can put breakpoints here. So let me put breakpoint here, and let's run it. Cool. Oh, it was subtracting 2 before as well. Wait, was I supposed to set the carry flag? Wait, what happens when there's no... Is this an inversion of carry, actually? I didn't know. Wait, how does subtract with borrow work again? That doesn't really seem like that's how it should work. Why is that not how it works? Yeah, because this actually adds carry, but the other one subtracts the inverse of carry, it looks like. Oh wait, because if m was less than a, then the subtraction gets turned into something like an addition, and then there's an actual carry involved, and so you have to do the inverse. So I have to do the inverse. Okay. So I sort of get it now. That was just a bit disorienting before. So I actually have to set the carry flag. Sure. Link it and oh, right, okay. Exit. Okay. So we're still getting corruption. We actually got some cool sounds. Okay, sure. Let me step through a little here. That wasn't it C0 before? B4, B3, B2, B1, B0, 8. Four, three, two, one. What? Wait, hold on. Hold on. Did I? Is like the decimal flag? Oh my gosh, it is set. I've been doing decimal arithmetic. This is so cursed. Right? That's how that works, right? 6502 decimal flag. Yep. Okay, so I have to unset that. Cool. By the way, just to check, the other instructions didn't. Yeah, they don't affect the decimal flag. I think that's just something you have to set. Which I'm not sure why that's set to 1 by default, but whatever. We can deal with that. Might as well do it at the beginning, I guess. Not sec. What is it? Is it skill D? Yes. So I want to clear the decimal bit. Okay. Let's do this again. It's crazy behavior. All right, let's do this again. Still doesn't look quite right. I guess it's not crashing as often. That's a positive, I guess. But it's also not being consistent either. Now we got an invalid instruction. Oh. There we go. Rewind. Okay. Let's try this again. Run it until here. And the decimal flag's clear, right? Yes, it is. B, D, C, B, A, 9, 8, 7, 6, 5, 4. Oh, wait. Isn't there supposed to be a W sync in there? There is. Lol. So let's put that in there. STAW. STAW sync. Ooh. We actually had the thing though, right? Yes. We had epilepsy screen. Okay, now I want to cause crash. Okay, why did it crash? Rewind. Run. Right, so it's going down. Yep. Okay, sure. Now how about I skip all that and we run here? Okay, yes, so we have the screen. And so... Oh, I forgot the backwards jump. That's why. What is it? JP entry? Yes, JP entry. I think this should be fine after this. Unknown symbol entry. The instruction is called JP, right? You can fix your finances at JP Morgan and Chase, I guess. Where's it? Jump? Oh, it's JMP. Okay, sure. JMP. Oh, I guess I forgot that the 6502 had this pattern where literally every instruction is a 3-letter acronym, so I could have known that from that. There we go. Beautiful. Look at that. We're doing colors. Yay. Let me add to my get ignore. Apparently it doesn't do bins, so I'm surprised it doesn't actually do bins. Especially because this is like the default, what is it? It's the default get ignore for C and C++. You would think bins would be included, but I guess not. What is it? Draw colors to background. Yay. Okay, huzzah. This has been fun. Let me pause this. And let's see, was there anything else I wanted to leave off with? Yeah, not really. It's again, it was fun. And I hope to keep doing this. It's definitely not close to the Pong remake. Did I say I was doing a Pong remake? Yeah, that's what I'm gonna do for my first game. A Pong remake. In case I didn't say that before, I forgot. But anyways, yeah, it's still a long ways from that, but it's a good first step. It's very cool. Drawing things on the screen. All right. And also the colors just having a bunch of colors is just kind of a strong showing of the Atari in general. I think it's a neat little trick. Well, other processors can do this trick, but still, just like the Atari having the resources it has and being able to do that sort of trick is actually very cool. Yeah, anyways, that's it.